Today, we are diving deep into a really fascinating corner of the AI world, model pruning. You know, we all want AI models that are smaller, faster, and more efficient. But when you shrink them down, you often pay a pretty steep price in performance. So we're going to break down exactly why that happens, and more importantly, we'll explore the incredible techniques researchers are now using to bring these pruned models right back to life.
All right, so let's jump right into the central problem here, what some people call the pruning paradox. On one side, the benefits, man, you just can't argue with them. You prune a model and boom, it's smaller, it runs faster, and it costs less to operate. For anyone trying to deploy these things in the real world, that's a massive win. But there's always a but, right? There's a real cost. The model's ability to follow a chain of logic can just shatter. Accuracy tanks, and overall its performance gets seriously degraded. So the big question becomes, how can we get all of those amazing benefits without the devastating performance hit?
To figure that out, here's the game plan for our explainer. First, we'll really dig into the performance problem itself. Then, we're going to play detective and diagnose what's actually breaking inside the model. After that, we'll open up the recovery toolkit, check out some advanced strategies, lay out a super practical, step-by-step pipeline you can actually use, and finally, we'll take a peek at what the future holds for this whole field.
Okay, let's kick things off with pruning's performance problem. And yeah, while it is a problem, I want you to think of it differently. It's actually a massive opportunity, a total research goldmine for anyone who's interested in making AI way more efficient.
Now this right here, this is probably the single most important idea to get your head around today. When you prune a model, you aren't actually erasing what it knows. You're not deleting its understanding of, say, language or complex ideas. You're just removing structural capacity, the neurons, the connections. The knowledge is still in there, it's just lost. Kind of like having a massive library where someone's gone and completely scrambled the card catalog. The books are all still on the shelves, but good luck finding anything.
And this is where it gets really cool. Look at the efficiency of the fix. It turns out you can get back the vast majority of that lost performance using less than 5% of the original compute it took to train the model in the first place. That's not a small tweak, folks. That is a straight-up game changer. It means this recovery process is an incredibly high-leverage move.
So, if we're going to fix this thing, we have to understand what we're fixing. This next part is all about diagnosing the damage. We're going to peek under the hood and see what's really going sideways inside that model's architecture.
So this is the million-dollar question, right? When we chop out all those parameters, what is the actual mechanical failure that causes performance to just drop off a cliff? Because it's not as simple as just saying, oh, we made the model dumber. It's more nuanced than that.
The damage is actually pretty specific. First, you get this distribution shift. The signals that are bouncing between the layers of the network, we call them intermediate activations, they start to look different. The next layer is expecting one thing and it gets something else entirely. Second, those residual streams, which are like these information superhighways that let data skip layers to preserve context, they get all misaligned. And finally, the model might just lose the ability to spot rare but really important features because the specific neurons that handled those are now gone.
And this quote just brilliantly reframes the entire issue. The model isn't broken beyond repair. This isn't catastrophic. It's a representation mismatch problem. Think about it like you're working on a complex engine, and you swap out a part. The new part might be perfectly good, but the whole system needs to be recalibrated around it. So the big insight here is that recovery isn't about relearning everything. It's about realignment.
Okay, so we've diagnosed the problem as one of alignment. Perfect. Now let's open up the recovery toolkit. We're going to focus on two really powerful, really practical techniques the researchers use to get all those internal parts talking to each other properly again. Our first tool is called knowledge distillation, and the idea behind it is just so elegant. You take your original big model and you call it the teacher. The new prune model, that's your student. Now, during a really short recovery training phase, you teach the student not just to get the right answer, but to think like the teacher. It actually tries to match the teacher's level of confidence across all the possible outputs, so it's learning the subtle reasoning behind the answers, not just the answers themselves.
The second tool, and one that's become a huge favorite in research lately, is LoRA, which stands for low-rank adaptation. And really, this table just says it all. If you do a full fine-tune, the compute cost is high, the risk of overfitting and messing things up is high, and you're changing every single weight in the model. LoRA is the exact opposite. It freezes all the original weights and just trains these tiny, super efficient adapter modules. It's surgical, it's cheap, and it's fantastic at avoiding overfitting, which makes it absolutely perfect for this delicate job of realignment.
And here's what that workflow looks like in the real world. It's beautifully simple. Step 1, you prune your model. 2, you apply those LoRA adapters specifically to the parts you just pruned. 3, you run a short recovery training session on some data. 4. You merge the trained adapters back into the main model's weights. And 5. You're done. You've got an efficient, high-performing model that's ready to go.
So, we've got our basic toolkit down. Now let's level up and look at some more advanced strategies. Think of these as safeguards and some of the more cutting-edge, experimental stuff that researchers are playing with to make this whole recovery process even more powerful. So here's a pretty wild idea: elastic width transformers. Instead of just fixing the damage after we prune, what if we could make the model tough enough to handle pruning from the very beginning? The concept is basically to train the model to work correctly even when parts of it are randomly switched off. You do this by just randomly dropping neurons during the training process itself. It's a proactive approach, and honestly, it's a huge research opportunity because if it works well, it could make this whole recovery step totally unnecessary one day.
Now here's a critical thing to watch out for during recovery. It's called catastrophic forgetting. This is what happens when, in the process of fixing the pruning damage, you accidentally cause the model to forget all the general knowledge it had before. It's like you're so focused on fixing one thing, you break something else. But you can prevent this. Use a good mix of data, keep your learning rates low, and use knowledge distillation to keep the model anchored to its original brain. The rule of thumb is simple. Recovery should be a gentle nudge, not an aggressive shove.
Okay, time to put all the pieces together. This section is probably the most actionable part of this whole explainer. It's a clear, reproducible, step-by-step blueprint that researchers can use to set up an effective recovery pipeline in their own work.
And here it is, the 6-step pipeline. Step 1, perform structured pruning on your model. Step 2, apply those LoRA adapters to the parts that were affected. Step 3, use the original model as a teacher for knowledge distillation. Step 4, train for just 1 to 3 epochs. That's it. It's incredibly fast. Step 5, merge those adapters back in. And finally, Step 6, evaluate your performance. The whole thing is cheap, it's scalable, and it gives you really solid, reproducible results.
But listen, a successful recovery isn't just about getting a high accuracy score on a benchmark. To really, truly understand what you've done, you need to measure more. How consistent is its reasoning? How well calibrated are its predictions? How does it perform on those rare, weird, long-tail tasks? And this is critical. You have to report these metrics at 3 key points: before you prune, right after you prune, and then after your recovery process is done.
And this right here, this is what success looks like. This chart tells the entire story perfectly. You start with the original dense model, way up there with high reasoning performance. Then you prune it, and wham, performance collapses, a massive drop. But then, after running our recovery pipeline, look at that. It shoots right back up, almost to where it started. That is the power of precision recovery and a single image.
So for our last section, let's look to the horizon. Because model recovery isn't just some cleanup job you do at the end. It's becoming its own vibrant, essential field of research that's really shaping the future of efficient AI.
There are so many cool and exciting open questions on the table. Like, can we design pruning methods that already know they're going to be recovered later? Could we customize the recovery tuning based on the specific prompts a model is likely to see? How do we make absolutely sure that recovery doesn't mess with a model's safety alignments? And could we maybe do all of this realignment without even needing adapters? These are the big questions that are going to drive the next wave of innovation here.
So, to wrap it all up, let's come back to this central idea, this core metaphor. Pruning is a structural operation. You are physically removing parts of the model. But recovery is an alignment operation. It's that delicate fine-tuning process that gets all the remaining pieces working together in perfect harmony again. And you have to realize that skipping recovery isn't being efficient, it's just leaving a ton of free performance sitting on the table.
And that leaves us with one last kind of mind-bending thought to chew on. If we can remove 30, 40, maybe even 50% of a model's parameters, and then bring its performance almost all the way back with such a tiny, tiny amount of compute, what did we actually remove in the first place? Was it truly essential structure, or was it just redundancy we didn't need? It really forces you to rethink what we even mean when we talk about making AI efficient.